My name is Jonathan Afek, and I work on the Watchfire security team. I'm going to present to you research we did about dangling pointers. So, dangling pointers is a well-known class of vulnerabilities, but so this is not new. But what is new is the 3 new exploitation techniques that we have researched and developed at Watchfire. And on top of that, I'm going to show you a real-world dangling pointer vulnerability in the IIS 5.1 web server, and I'm going to show you how to remotely exploit it. So, let's begin. First, I'm going to tell you what is a dangling pointer. Explain what is this vulnerability. Afterwards, I'm going to talk to you about some technical background needed in order to understand the exploitation techniques, and I'm going to show you the exploitation techniques themselves. Afterwards, I'm going to show you the demonstration of the remote exploit. Then I'm going to talk a bit about what can we do in order to defend ourselves. Then I'm going to summarize and let you ask some questions. So, actually, this presentation is going to be technical. I'm going to explain all the things needed in order to understand this presentation, but it is technical, so pay attention to the details. So, what is a dangling pointer? Actually, every dereference of a pointer that points to invalid data is a dangling pointer vulnerability. I'm going to talk about a specific dangling pointer vulnerability that I'm going to show you with the next animation. So, let's imagine an application that has 2 pointers, pointer 1 and pointer 2, that each one of them points to a different data object. Every application has some pointers and some objects, and this is just an example. Let's imagine the application executes the next line of code. This code creates a new object instance in the application's memory, and a new pointer called pointer 3 that points to this object. Now, after the application finishes to use the object, it deallocates it from the memory in order to save system resources, because the application needs to save memory. But the pointer is still in the memory and points to a place that has no longer valid data. So this is a dangling pointer. Now, when the application uses this pointer, it actually... what's that? Okay, so we got a crash. So this is the usual behavior when you try to dereference a pointer that no longer points to valid data. So a bit about exploitation. I'm going to show you 3 exploitation techniques, actually. And a common thing to all of these exploitation techniques is that... what is that? That we're going to intercept in between the deletion of the object and the execution of the virtual function, the function that relates to this object, and overwrite the object, the memory location where the object used to be. So in order to illustrate it, I'm going to show you an example. For those of you who are unfamiliar with VMware, this software enables me to run another machine on top of my Windows XP. So here I have a copy of Windows XP that only has the only thing that I did on it is install IIS 5.1 on top of it. This Windows is fully patched as of last month. And it is vulnerable to the dangling pointer vulnerability that I'm going to show you in a moment. So I'm going to browse to this web server, to the IIS web server that is on top of the inner Windows. I'm going to call this the VMware Windows. So I'm going to browse to the web server that it runs. Just a moment. Okay, so the only new thing that I have put inside the web server is an ASPX, just an example ASPX page. It could have been any other ASPX page. And besides that, it's just the default installation of the IIS server. Okay, so I browsed to this ASPX page, and this communication with the web server made it allocate a new object. If I just send 3 more requests that looks like this, it deallocates the object and still keeps a pointer that points to it. So now I have a dangling pointer inside the application's memory. Okay. Now I'm going to make the IIS server execute a virtual function that relates to this object, and we're going to see the results. Okay, so this is the behavior I talked about earlier. This is what usually happens when you try to execute virtual functions using a pointer that no longer points to a valid object. Okay, so as I told you before, all of the exploitation techniques that I'm going to talk about, in all of them, I override the object in this place. I'm overriding the place where the object used to be with my own data, and therefore I can make the application use my own data as if it was the object. A few things about dangling pointers. As I'm going to show you, dangling pointers are very dangerous, and I think most of them can be exploited for arbitrary code execution. So they are exploitable, and there is a good methodology in order to exploit them. And they are common. As I've talked to many C++ developers, I realize this kind of bug is very common, and sometimes it is even harder to detect than regular buffer overflows and other bugs. Because sometimes the application won't crash when you execute the virtual function and will just look like as nothing happened, but you can still exploit it. Okay. So a few things we need to know before we can talk about all the exploitation techniques. A few terms. The first one is memory layout. So we need to understand that each application has a memory layout and that it has memory addresses. So let's take, for example, the memory address that you can see on the left, 00920050. This address points to the beginning of this buffer. It points to the byte 45. These are all hexadecimal digits. So each 4-byte value can be treated as a memory address and can actually represent a place in the memory. In the rest of this presentation, I'm going to use the size 4 bytes a lot of times. So whenever I say a D word, you probably know it. I mean 4 bytes. Another thing is registers. Those of you who are not familiar with the term registers, registers are CPU variables, actually, that can usually, to simplify things, they can hold D-word values and can hold pointers to places in the memory. Okay. So as I told you before, I'm going to inject new data instead of the old data that used to be to reside in the memory. And in this section, I'm going to show you what is the new data that I need to put instead of the old one. So before we begin, we must first talk about how does an object instance look like in the memory. So let's take, for example, this class definition. Okay, so now we have the definition of class A. It has an integer member, 3 virtual function, 1 static function, and 1 regular function. Okay? This is how an instance of this object looks like in the application memory. So each rectangle in this small rectangle in this diagram represents a D word, and I'm going to start from the left to the right. So the most left thing in this diagram represents the instance itself of the object. As you can see, the static functions and the regular functions are not in this diagram, and they do not reside inside every object instance. The first D word of every object that has virtual functions is a virtual function table pointer. Okay? And after that, we have all the variables of all the members of this object. So the virtual function table pointer actually points to the virtual function table. This is the thing that I'm pointing out. The virtual function table resides of addresses of all the virtual functions of this object. As you can see, the first D word of this table has the address of the first virtual function. The second D word has the address of the second virtual function. And the third D word has the address of the third virtual function. Okay, so let's see what actually happens behind the scene when the application executes this line of code. It actually is compiled to something very similar or equivalent to these assembly lines. So whenever an application uses an object, it usually points to the beginning of the object with ECX. ECX is a register that can hold a D word value, that can hold a pointer in the memory, and it usually points to the beginning of the object. The first assembly line makes EAX, which is another register, point to the beginning of the virtual function table. And the second assembly line actually executes the third virtual function code, because EAX points to the beginning of the virtual function table. EAX plus 4 points to the second D word of the virtual function table, and EAX plus 8 points to the third D word of the virtual function table, and that is the address of the third virtual function code. Okay, so this is how objects are implemented. Now I'm going to show you the first exploitation technique that I'm going to talk about. In this exploitation technique, I'm going, as I did before, to make the application allocate an object. I'm going to make it deallocate this object. Afterwards, I'm going to overwrite the place where the object used to be, and then I'm going to make it execute a virtual function. Okay, so object allocation. So first of all, I'm going to make it allocate a new object, just like I showed you when I sent the first request to the web server, that is in my VMware. Then I make the application deallocate this object, as I showed you with sending three more requests to the web server. Then I override the object. So I'm not. The next section is dedicated to this subject, so I'm not going to tell you now exactly how can I overwrite the same location exactly. And we're going to talk about the content that I'm going to put in it right now. But it usually happens, in order for you to understand it, when I found another place in the application where it allocates buffer of the same size of the size that the object used to be. Okay, so we have two parts to the new content that we insert instead of the old object. The first part is the shellcode. We just insert the shellcode there because we need to insert it someplace. This is the code that we want the application to execute. This is our code, our malicious code that we would like the application to execute and therefore enable us to take over the vulnerable machine. And the second part is our fake virtual function table pointer. We're going to put a new virtual function table pointer instead of the old one. So, as I told you, ECX usually points to the beginning of the object when the application uses objects. Wouldn't it be nice if we could find a way for the application to execute call or jump ECX, and by that make it jump to the beginning of the buffer and execute our shellcode? So I'm going to show you how to do that. First of all, we need to find a place in the memory that has call or jump ECX. Each one of these assembly lines consists of 2 bytes. There is a really good chance that we can find lots of this instruction randomly inside the application memory, and we just need to use one of these locations. We need to use a location that for it I can also find a pointer that points to this location. So this is a difficult task to do, because what are the chances that you're just going to randomly have a pointer that points to another location inside the memory? But this is possible because we have so many call or jump ECX that enables us to just find another. One of them has another location that points to this memory address. So after we found a pointer that points to the call or jump ECX, we just take the address of this pointer, subtract it by 8, and put it in the virtual function table pointer. This will be our new virtual function table pointer, and this will enable us to make the application think that the third virtual function code is actually call or jump ECX. So now when the third virtual function will be executed, as I showed you earlier in the example by shutting down the server, what I did inside the VMware, when it will be executed, it will actually execute my new inserted code and enable me to run my malicious code. So here we have again the code that runs when the function is executed. ECX points to the virtual function table point, to the beginning of the original object. The first assembly line makes EAX point to the beginning of the virtual function table. And then when the application executes call EAX plus 8, it will actually jump to the beginning of our shell code. What?
When you jump to ECX, aren't you fetching your vtable pointer?
Yeah, so the question was, I'm actually executing the virtual function table pointer as code, and that's a problem. That's what you meant?
Yes.
Okay, so usually, I just was about to talk about that. Usually when random bytes are interpreted as code, this is really a problem. But randomly, as I did it, I tried to run many pointers as code when I researched this exploitation technique, I saw that most of random assembly instructions just do not influence dramatically on the execution flow of the application, and it would just execute it and continue to execute my shellcode that just resides afterwards. Okay, so how can we overwrite this object? That's the subject of this section. I'm going to talk a bit about how allocation is implemented, memory allocations are implemented, and deallocations inside Windows applications. So each application has a C runtime heap. This heap is actually part of the memory layout that I talked about earlier. This part of the heap is used to hold data objects that are allocating using the new operator and the malloc function. And actually each allocation that happens with one of the functions that you can see on the slide is performed inside the C runtime heap. Okay, so another thing about allocation implementation is what the application does when it deallocates an object. So the application could return to the operating system each buffer that it deallocates, but that would be inefficient because the application will later want to allocate another buffer of the same size. And it would be inefficient to ask the operating system to provide another buffer of this size. So each application has allocation cache. It saves the deallocated buffers somewhere in the memory, and then when it tries to allocate buffers of the same size, it just takes it from there. So this feature is called a look-aside list. Each application has a different look-aside list for each size between 8 and 1024 in jumps of 8. And so this is the first allocation priority. When the application wants to allocate another object of the same size, the first place it will look in is the look-aside list. So let's see an example and make you understand a bit complicated thing called look-aside list. So this is an example look-aside list. The look-aside list for 40 bytes buffers. So this look-aside list has just one buffer inside it right now. Let's say the application deallocates another buffer in size of 40 bytes. So this is how the look-aside list will look like now. Each item of the look-aside list has in its first dword a pointer to the next buffer of the look-aside list. And the last buffer of the look-aside list has null instead of the pointer. Then that means it points nowhere and that it is the last item of the look-aside list. Let's say this application wants to allocate another buffer of 40 bytes. It will just take the first item of the look-aside list and use it as the buffer it wants to allocate. So whenever an application deallocates a buffer, it inserts it to the beginning of the look-aside list, and whenever it allocates a new buffer, it takes it from the beginning of the look-aside list. Okay, so this is the look-aside list. How is this relevant to the double reference exploit? So this is what we previously did. This is a short review about the double reference exploit that I talked about earlier. I make the application allocate a new buffer using the first request that I sent to the server, to the web server. Now this is just an example. I'm talking about dangling pointers in general, and I'm using this example to illustrate how it is done. So I send the first request and make the application, the IIS application, allocate this buffer. Then I send the three more requests, and I make the IIS server deallocate the buffer. I make the application deallocate the object, and then I have a dangling pointer that points to the object. And between the execution of the virtual function, I override the object, and now I'm going to talk about how it is done. So every big enough application will have many allocations inside it, many execution flows that inside it that result allocations of the buffers of the size that the object used to be. So I just disassemble the code, find these kind of allocations. And another limitation is that I need the newly allocated buffers to have controllable content. I need that as a user, I will be able to control the content of these allocation. Now, I think that every big enough application, for example, the IIS web server, has this kind of, I can find many of these kind of allocations inside it. Now, the IIS specifically is a bit complicated because of another thing that I will not get into right now, but I'm going to show you an example for this in the IIS web server. So let me just start the server again. So we're going to start like in the example I showed you earlier. First of all, I browse to the ASPX page. This makes the IIS web server allocate the new object. Then I send 3 requests to this URL. This makes the IIS web server deallocate this object. Now, what I did just now is insert a new configuration item into the IIS configuration. Now, this is not the remote exploit that I talked about. This is just an example of the double reference technique. And this is a local exploit because it requires me to insert a new configuration item into the IIS web server. And the details are in the white paper, so I'm not going to talk about exactly what configuration item or what I exactly did. But I inserted a new configuration item. By sending 2 more requests, I'm going to make the application allocate the newly inserted configuration item. And this configuration item is just in the size that the object used to be. And it consists of the data that I showed you earlier in the double reference exploit. The first 4 bytes of the new configuration item is the new virtual function table pointer, my fake virtual function table pointer, and the rest of it is my shellcode. Okay, so 1 request, 2nd request. So now when I stop the server, let's see what happens. Yes, my shellcode created a new file called hacked AAAA. So this shellcode could have been anything, and this is my malicious code running on top of the vulnerable IIS 5.1 web server. Okay, so this is the 2nd exploitation technique, and it is called the virtual function table exploitation technique. sometimes it is hard to find allocations in which you can control the first D word of these allocations. Because usually you'll find allocations that are used in order to create new objects. Each new object will have its own virtual function table pointer. So even if you could control the content of the members of this object, this newly created object, it's sometimes harder to control the first D word of this new buffer. So in this exploit I have different requirements, but I solve this kind of problem. So using this exploitation technique, I can still exploit by dangling pointers vulnerabilities that in application in which I cannot control the first D word of the new allocation. In this exploit, I require another thing. I need to be able to control many allocations and deallocation in the applications. For example, a web server, when serving specific web pages that contain specific JavaScript, can control allocations and deallocations of users that browse to this web page. This information can be found, and I was influenced by the paper called Heap Feng Shui in JavaScript, published by Alexander Sotirov. I hope I pronounced the last name right. So this is just an example. I think that in many large enough applications, I can be able to remotely control allocations, but this example shows the fact that when using an application from a remote location, I can control allocations and deallocations. The JavaScript code that runs inside the browser can control the buffer allocations of the browser itself. So, first of all, I'm going to make the application empty the Leukocyte list of the relevant size. How I'm going to do that? I'm going to make the application make many allocations of the same size of buffers of the same size. Then I'm going to allocate a new buffer, make the application allocate a new buffer. Afterwards, I'm going to insert this content into the newly allocated buffer. So I don't have to actually control the first D word. I can hope it will contain data that when interpreted as code will not be of any kind of trouble for me to execute. But I should be able to control most of the buffer. I put this pointer to a location that has call or jump EAX. This time it is EAX and not ECX, because this buffer is going to be the virtual function table, the new virtual function table of the object. Okay. So the next step will be to deallocate this buffer, and it will be inserted into the leukocyte list. You can see the leukocyte list in the diagram. Then I'm going to make the application deallocate the object, like I showed you earlier by sending the 3 more requests to the web server as an example. So now I have this object. I have this object that is pointed by a dangling pointer. That when interpreted as an object, it has a virtual function table pointer that points to my fake virtual function table that has in is the third D word pointer to call or jump ECX. So this is actually the code that that is relevant to the third virtual function. So this is the code that runs when I execute a virtual function. So I have the ECX register point to the beginning of the original object. The first assembly line makes EAX point to the beginning of the virtual function table. And the second assembly line actually executes call or jump ECX and makes the application jump right back to the beginning of the virtual function table and execute it as code. This is no longer a virtual function table for the application. This is now code that it will execute. So this is how I execute my shell code in the second exploitation technique. Okay, so now we had two exploitation techniques by now, the double reference exploitation technique and the virtual function table exploitation technique. And I'm going to show you the third one. The third exploitation technique is a bit special because it makes it you do not have to have some requirements you had to have in the previous exploitation techniques. And I'm going to first show you the exploitation technique and then talk about what is so special about it. So just like the previous exploitation technique, I'm going to make the application empty the look-aside list. I'm going to do that by making it allocate many buffers of the size of the old object. Then I'm going to make the application allocate two buffers of the same size. This can be done just like I showed you, just like I told you earlier, the heap function in JavaScript proves this. This can be done specifically in the situation of browser, but I believe this can be done in many applications and can be controlled remotely in large enough network applications. Then I'm going to insert my shellcode into one of these buffers, make the application actually insert my shellcode. As you remember, I'm searching for controllable content allocations and not just allocations of the same size. Then I'm going to make the application deallocate the buffer that holds my shellcode. Then I'm going to make it deallocate the other buffer I just allocated. And then I'm making it deallocate the original object. So now, look at this diagram. I have the dangling pointer pointing to the beginning of this object that now holds a fake virtual function table pointer that points to a fake virtual function table. That the first function pointer, actually what would be considered as the first virtual function code, is actually my shellcode, the shellcode that I inserted. So what is so special about this exploitation technique? This exploitation technique enables me to exploit dangling pointer vulnerabilities without finding first call or jump ECX or EAX in the application memory. I do not need to count on the fact that I will have these instructions found randomly in the memory. Then I'm going to trigger the bug, make the application execute the virtual function, the first virtual function, and by that run my shellcode. Other note, I want to say to you that most of the times the first virtual function will be the destructor, the virtual destructor of the object. And as most good C++ developers know, every object should have a virtual destructor, and by that I can count on the fact that it will probably have a virtual destructor, and this makes this exploitation technique very likely to be used. Game over. Okay, so in the last exploitation technique, the first 4 bytes of the shellcode was actually zeros, null, and this is not any problem to me to execute because it just influences the content of what EAX points to. But that's if you can remember, EAX pointed to the virtual function table, which was I have no problem for it to be changed. Okay. So let's talk a bit about the exploits. We had the double reference exploit. In this exploit, we needed to find the locations in which we can control outside of the application the first D-word of those allocations. We needed to be able to control the new fake virtual function table pointer. And we needed to find inside the application memory call or jump ECX and use it afterwards. We had several more restrictions to the specific address we found. We needed to find another pointer that points to the location where the call or jump ECX was in the memory. And this was the double reference exploit. We had the virtual function table exploit. In this exploit, we needed controllable allocations. We did not actually need to be able to control the first D-word, but we inserted our shellcode in these allocations, and we need to be able to control allocations and deallocations and not just allocations like in the double reference exploit. And we still needed to find the static place in the memory that holds call or jump EAX. And we had the look-aside list exploitation technique, in which we still needed to have controllable allocations. We needed to be able to allocate 2 buffers to insert our shellcode into one of them and to make the application deallocate both of these buffers. We did not need to find a static location in the memory that holds jump or call ECX or EAX, but we needed to be able to make the application execute the first virtual function, which will usually be the destructor, and we couldn't do it on any virtual function, just the first one. Okay, so probably the moment you've been waiting for, the demonstration of the IIS 5.1 remote exploit. A few words about this application, about this vulnerability. So this vulnerability was publicly known since December 2005 and was fixed in the last patch Tuesday, which was on July 10th, 2007. This emphasizes the fact that dangling pointers are usually I don't want to say usually, but I see a lot of people that do not consider them as major security issues. It was said that this specific issue can only be used as is a DOS vulnerability, denial of service vulnerability. I personally think that denial of service vulnerabilities are very serious, but code execution vulnerabilities are much more serious. So it was fixed the last patch Tuesday. After we showed the newly discovered implications of this vulnerability, that it can be exploited for arbitrary code execution, Microsoft issued a patch very efficiently and fast. And enough talking about this application, I'm just going to show you the exploit. So here we have the IIS 5.1 web server. It is not patched as you saw in the previous examples. It has nothing on it besides the ASPX I browsed to earlier. And this ASPX page could be any ASPX page. It has nothing special in it. So this is just a default installation of IIS 5.1. So Once again, I'm going to make the application allocate the new object. Now I made it deallocate the object by sending the 3 requests. Now, I'm just going to send a few more requests, and I'm going to use a tool called tamper data in order to do that. It's not really important that the technical details are inside the white paper that you can read. I'm just going to do some fast request sending, and the technical details can be read, and nothing really relevant to the presentation. So, tamper data. So, as you can see, the server is still up. We have a crash window, but as the server is still responding, as you can see, and this means that one of the threads of the application just crashed, but the application is still running if I do not click on any of these buttons. Now, when I shut down the server, you've been pwned by Watchfire, an IBM company. Okay, so this was my code. But you might still consider me a liar because I needed to run netstop W3 SVC on top of the vulnerable computer. And that is called a local exploit and not a remote exploit. I consider it to be a remote exploit because this code will run whenever the server stops. Every web server administrator sometimes reboots the server or shuts down the service of the server, and actually we get the same behavior when the server reboots. So we can just make the application make the dangling pointer point to our newly inserted object, and by that, when the administrator reboots the web server, it will execute my newly inserted shellcode. In this remote exploit, I did not use any of the previously talked about exploitation techniques, because it was hard to implement this specifically remotely in this application. But this just show you that if you look deep enough inside the allocations of the specific application that you're trying to attack, you'll eventually find a way to exploit it. So what I'm saying, take dangling pointers very seriously. Okay, so what can we do in order to protect ourselves? There are some known protection mechanisms, such as the NX bit. The NX bit enables you to define some memory pages as executable and some as not executable. So when the application tries to execute the pages that are marked as non-executable, it will actually crash and not continue to execute it. So on each of the previously showed exploitation technique, the NX bit will actually save the vulnerable application from executing the inserted shellcode. A specific variation of the double reference exploitation technique can be done in order to exploit the systems that do use the NX bit protection mechanism. Next, we have the ASLR protection mechanism, which actually randomizes the memory layout of the application. And when it is used, you cannot reliably find static addresses that holds jump or call ECX or ECX inside the application memory. This protection mechanism can be overcome using the third exploitation technique, the look-aside exploitation technique, as I showed you earlier. The second, a suggestion I have is virtual function table sanitization. Compilers can compile objects that, when executing virtual functions, sanitize the value of the virtual function table pointer and make sure that it does not point somewhere weird, and protect the application this way. And of course, the only true protection mechanism that can defend us is safe programming. We just need to develop safe software, because other protection mechanism can help and can be really efficient, but we will always find ways to overcome these protection mechanisms. Okay, so what did we have? First of all, we talked a bit about technical background. We talked about memory allocations, how it is implemented, about the look-aside list, and about object implementation. How does an object instance look like in the memory, inside the application's memory? Then we talked about 3 exploitation techniques: the double reference exploitation technique, the virtual function table exploitation technique, and the look-aside exploitation technique. Afterwards, I showed you a remote exploit of the Microsoft IIS 5.1 web server, and that was it. Another thing I want to say is that this research was performed on a specific kind of dangling pointers. There are other kinds of dangling pointers, and some research has been done in this direction in the community, the security community. And I think more research can be done, and other bugs might be proved as generally exploitable for arbitrary code execution. I think that every bug should be treated as every serious bug should be treated as major security issues, and developers do not need to wait until these kind of bugs are proved as exploitable. Another thing I want to say is, just a few days ago, I found actually another dangling pointer vulnerability, just like this one that I found, and I later found out that it was previously known since December 2005. So I searched the web for this newly found vulnerability, and I found that this vulnerability was previously known also. I'm not going to talk about the details because we hadn't had a chance to contact the vendor yet, but this is interesting because this was too a dangling pointer problem that was known to the vendor, and he did not fix it. So this emphasizes the fact that sometimes dangling pointers are taken not very seriously and considered less dangerous than other bugs. Okay. More information can be found on the Watchfire website. You can find the updated white paper that we published with all the technical details inside it on this website. I also want to note Adi Shahrabani, who helped with this research and managed it. And that's it. Ask away. Any questions?
From a remediation perspective, would you consider just clearing out your pointer to make you say, if you deallocated it, set it to null, and you're okay, or do you need to do more than that?
So the question was whether a good remediation would be to null the pointer to the object after you deallocated the object. So you will not have a dangling pointer that points somewhere in the memory. It will have the value of null. Well, if I can make the application use this pointer as a pointer object, as an object pointer, excuse me, so I can still crash the application. I can still make this a denial of service situation because it will use null as a pointer to an object. I cannot think of a way now to exploit this kind of situation, but I would say I don't know how to exploit this kind of situation. It can improve your security, but you should not rely on this as a security measure. Yes?
First of all, I would imagine that these are all over the place in software, and just being, as you said, treated as if they're everyday old bugs. But I imagine they're probably everywhere. Have you been able to define, in some sense, certain patterns for how you could find these kinds of issues? I mean, I imagine you're basically involving certain sequences of allocations and deallocations that are perhaps detectable in code.
So I guess everyone heard the question. He speaks very loud.
I have that happen. Wait till tomorrow.
Yeah. Okay, so actually the answer is that I do not have a specific pattern in order to detect this kind of vulnerabilities, but I said previously that this kind of vulnerabilities are sometimes hard to detect. Not every time when you deallocate an object, it gets inserted into the look-aside list I talked about earlier. And if it does not get into the look-aside list, sometimes just the first keyword of the object is not changed. And therefore, when it tries to execute a virtual function, it will still run the old code of the virtual function. And you would not know that this application is vulnerable to dangling pointer vulnerability. But as an attacker, you can still use the exploitation techniques and exploit it. So I do not have a good way to detect this kind of... Yes?
During the demonstration, you were rather careful to not close the crash window.
Yeah, that's right. So the question was, why was I careful not to close the crash window during the demonstration of the remote exploit? I did that because once I click on the application crash window, I actually terminate the application, and it will not be able to execute my newly inserted virtual function when it is terminated. So.
Two questions. First one, if you make use of the look-aside list in your exploit to steadily locate specific amount of buffer in your exploit, that's the first question.
Oh.
The second question is whether how do you find to allocate a specific amount of buffer using would it be possible using the chunk recording? And then the last one may be like, have you tried the community debugger? You have features to do like imaging. And finally, there is some discussion about now function your reverse exploit. You can basically locate the first page of the memory using a malloc. And then when you do a reference on the malloc, it will try to decode the zero page.
So, actually, I am too not a native English speaker, so I had a hard time understanding the question, but I will be happy to discuss this with you.
Should I repeat it? I'm sorry, my English is not good. Is it clear the question, or should I repeat it?
Yeah, you can try to repeat it, but if I will not understand it again, I would like us to talk about it afterwards. Yeah.
Yeah, the first question is like whether you use some technique to specifically allocate a fixed amount of buffer in your exploit.
Yeah.
You need to do that if you want to feed the local-side table. So whether you use that. First question, right?
I would suggest we talk about it afterwards because I didn't get it. Yes.
Why would the destructor be called again to exploit the runner code? I saw the Netscope and
Yeah, okay. So the question was, how can I rely on the fact that I get the destructor to be run after I imply the last exploitation technique I talked about? It was the Lucaside exploitation technique. Actually, I think that the application, after it uses an object, it will eventually try to deallocate it to run to destructor. So you might say the destructor was already run when the application the object was first deallocated. But if the application made use of this object again, I think it will try to run the destructor again. Sometimes it can be a bug of this nature. Yes.
I may have misheard you, but did you say that you didn't use either of those three exploits in the demonstration you just did?
Yes.
What did you do?
No, okay. So the question was, if I did not use any of the exploitation techniques I talked about, how did I do the remote exploit? That was the question?
Yeah.
So actually, researching the IIS 5.1 web server, I searched for a lot of allocations inside it, and I found another allocation besides the configuration item I showed you earlier. That actually I use it to exploit this vulnerability using the double reference exploitation technique. But besides this allocation, I found another allocation, which is of a very specific nature. I will not talk about it right now. This is actually detailed in the white paper that we published, and I'll be happy to discuss it with you after the presentation. No, I did not use any. Yes.
Does your white paper talk about the protection mechanisms you mentioned, like the NX bit and ASLR?
The question was whether the white paper describes that defense mechanism I mentioned, the NX bit and the ASLR, and the answer is that there is very good material about this kind of protection mechanisms on the net. So I do not describe it fully, but you can find very detailed explanations about it over the internet. Yes.
Could you at least remediate this problem by looking at it as a C++ runtime bug and change the C++ runtime where it would do that cleanup for the allocation? Nobody was calling it. Well, I guess you'd still be stuck with a denial of service potential, but at least nothing works.
Yeah, so the exploitation techniques I talked about are very specific, not to C++, but to object-oriented languages, unmanaged code, the object-oriented languages, like C++. The remediation that you suggested might make us not able to use the exploitation techniques I talked about. But every time you try to use you try to use an object after you deallocated it, it's a bug. So it doesn't matter how you look at it. Yes.
Does ASLR actually protect against the Lucaside technique, or because you aren't using static? You said that technique doesn't need static pointers.
Yeah. So actually, in the exploit summary, I talked about it. I said I do not need to find a static address. So that's the answer.
So ASLR would not work in that particular case.
Yeah, it would not defend the ASLR will not defend an application that has dangling pointer in it when the attacker uses the Lucaside list exploitation technique. Yes. Can you speak up, please? Are you here? So the question is that between the allocations I make the application do, can the application run specific code that will change the look-aside list in a way that it will no longer be valid as I showed you in the diagram? Yes, the application can do this kind of things. Specifically in the IIS, it does not have many random allocations and deallocations of this size, and you can just make. So this can be a problem, but I believe not a very big problem, and you can handle it when trying to exploit using these techniques in dangling pointer situation. Okay. Yes.
In all of your cases, you have to have local access to the machine, right? You have to have local access to the machine to be able to do your exploit?
So the question was whether I had to have local access to the machine in order to do my exploit. So the exploit I show you in the demonstration, I did demonstrate it using local access, but I told you why I think this can be treated as a remote exploit. Because the only thing I did on the local machine was to turn down the web server that will eventually be turned down anyway when the administrator will reboot the vulnerable web server.
But won't the heap structure change between that time?
What?
Won't the heap structure change in that time?
In what time?
Between you sending your exploit code and
Okay. So the question was, if I wait until the administrator rebooted the system, won't the heap structure change in the meantime? So actually, yes. I need to keep sending the last request I sent to the server in order to preserve the heap structure that I want to preserve. Okay. Thank you for being a great audience, and I hope you enjoyed the presentation.